Okay, so we are working on 10.3, which deals with chords. And what's going to happen is 10.3 is going to be the top two examples here and definitions. And again, you have your paper, and what we want to do is we want to start on the definition side and the theorems. So we can describe the theorems, and what I'm going to do is we'll go through one example here and then we'll flip it, and again you can have it folded already if you want to, or you can wait to fold it until after we are done, but I want to go through some of the definitions in these theorems, and that way I can show you and draw what these look like. So what we're talking about is chords. Now if you recall, a chord is just a line segment inside of a circle. So if I were to draw a line, say from right here to right here, that is a chord. Okay, a chord is just basically 2 points that are being connected in a circle, and it can be any 2 points in that along that circle that are connected. Okay, so what we're going to do is let's talk about this theorem. It says in the same circle or in congruent circles. So let's talk about the same circle first. It says in the same circle, two minor arcs are congruent if and only if their corresponding chords are congruent. So in other words, what we're looking at here is if I were to draw two chords, okay, and these aren't perfect, but they're going to be close enough. What it's saying is that if we're looking at this arc right here, we're saying this minor arc and this minor arc are only congruent to each other if the two chords are congruent to each other. Okay, so the idea of this is that we just are looking for either the two chords to be the same or the two arcs to be the same, and that will work. Okay, so that's if you have one circle. Now, the same thing is true if you have two circles. So we can draw a few things here. Let's draw a radius, and let's draw a chord. And I'm going to mark these now. And what we're going to do is we're going to do the same thing on this circle. And again, it doesn't really matter how we, where the radius is or where the chord is. But the point is that these are corresponding. These are congruent circles. How do I know they're congruent circles? Because the radiuses are the same. The radius will always tell you that two circles are the same. So this radius is congruent to this radius, therefore they are congruent circles. And now again, the same thing follows as before, because if we want the two arcs to be the same, then the two chords have to be the same. So anytime you have two congruent chords, you're going to get the congruent arcs of the minor arc. Okay, so that's the first theorem. Okay, the second theorem, which is again a pretty basic theorem, that says if one chord is a perpendicular bisector. So what we're going to do is I'm going to draw a chord. Okay, and then it says if one chord is a perpendicular bisector of another chord, then the first chord is the diameter. In other words, if I have this chord right here and I draw another chord that is going to be perpendicular, and again it may not look like it, but it's close enough. Perpendicular, remember, means right angle. So what it's saying is if I draw two chords in a circle, the first chord that is a perpendicular bisector has to be the diameter. It has to go through the center of the circle. So what happened is when I drew this line right here, it's bisecting these two lines, which means these two segments will be congruent, and it's also creating a right angle. Okay, so if it's a perpendicular bisector, it's creating a right angle, and it's creating congruent segments here. That means that this chord has to be a diameter. Okay, so in other words, if we have two congruent segments here and we know we have right angles, then we know that the chord that is doing that will be the diameter of it. Okay, so what I want to do is let's flip the paper over and let's look at these examples, and we will go through these. So the first example is saying find the measure. Okay, so we are given a circle R, and we're given that chord AB and chord CD are congruent to each other. Okay, and it's telling us that the measure of AB, so I'm going to label that right here, that's 108 degrees. So it wants to know what is, first of all, the measure of CD. Well, based on the theorem that we just did, or we just talked about, if the chords are congruent to each other, then that means that the minor arcs will also be congruent to each other. So the measure of CD is also going to be 108 degrees. Okay? Now we also want to, it also is asking to find the measure of CAD. Well, CAD, I'm going to do it in red, is going all the way around. Well, if you notice this, the only thing that we're missing from this major arc here, from CAD, is the CD. And because there's 360 degrees in a circle, we can say the measure of CAD will be equal to the total amount, which is 360, minus the amount that we don't have or that we don't want, 108, and that will give us 252 degrees. So hopefully that makes sense. Okay, the second one, this one's a little bit more difficult, so you're going to have to try and follow along on this one the best that you can. It says 3 props are placed on a stage at points P, Q, and R as shown. So we basically assume we're on a stage and P, Q, and R are props. It says, describe how to find the location of a table so it is the same distance from each prop. Well, to me, this is a very applicable problem, and it's important for us to understand how this would work. Well, based on the theorem that we just talked about dealing with perpendicular bisectors, what we're going to do is we are going to draw perpendicular bisectors of these points. In other words, I want a point that is going to, if I'm going to connect these, so that's the first thing, is let's connect this point right here, or these 2 points, and then let's connect these 2 points. What we're going to do is I want to bisect these lines. Okay, bisecting means cuts it in half. So I'm going to do the best that I can here. And again, it's not so easy to draw a straight line using this device here. Okay, so those are bisecting. I'm going to use a different color here. And now I'm going to draw a line that bisects these two. So what I've done is I've now drawn 2 bisectors. Well, based on what we just said, these are perpendicular bisectors. What we just said in the previous theorem, if we go back to that real quick, it says that if we are bisecting a segment, then what happens is that automatically becomes the diameter of a circle. Okay, so what we can do is we look at what we just bisected over here. Because we're bisecting, we can assume that this is going to be a diameter of a circle, and because we bisected this segment right here, we can assume this is going to be the diameter of the circle. So wherever those 2 lines meet would be the center of our circle. And that's what we want, because if that's the center of our circle, then what's going to happen is that's going to be equal distance from this point, it's going to be equal distance from this point, and it's going to be equal distance from this point. Okay, so I'm going to write that out real quick. What I'm going to do is, just so I can save time on the video, I'm going to pause it. I'm going to write out what you want to write down. Just hit, you're going to see it just pop up real quick, so that way we save time on this video. So you can copy it down. All right, so I've typed it out, so that way you can read it. It says the perpendicular bisector of each segment form diameters of a circle. So that's what we had done. Okay, so we did a perpendicular bisector here, formed a circle, or formed diameters of the circle, and then it says the point of intersection would be the center of the circle that would contain all 3 points. So remember, once we have the center of a circle, all of the points that lie on that circle will be equal distance away from that center. Okay, so moving on, let's go back to the second portion and talk about these theorems. So these theorems I think are a little bit easier to understand. So let me zoom in here so that way we can see this a little bit better. Okay, so the first one, it says, if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and the arc. So to me, this is a fairly straightforward idea. In other words, if I have a diameter that's going straight down and I know it's a diameter, and this is my chord. And what it's saying, if the diameter of the circle is perpendicular to the chord, so as soon as we know that it's perpendicular, automatically we know that it's going to not only bisect, which means this chord will be split up into 2 equal parts, but also the arcs will be congruent as well. It's also bisecting the arcs. Okay, so that's a pretty straightforward concept there. The next one, which is a little bit, it's a little bit tougher. I mean, it's not really difficult, but it's just one of those things that it's very hard to remember. This one says that in the same circle or in congruent circles, it says 2 chords. So I'm going to draw 2 chords here. It says 2 chords are congruent. So I'm going to mark them as congruent if and only if they are equidistant from the center. Well, the one thing that we have to realize is that to figure out the shortest distance between the center and a chord, it's got to create a right angle. Remember, the shortest distance between one line and another point will always be a perpendicular line. So the point is that if we know that 2 lines are perpendicular to our chord and they go to the center and they're the same distance away, then that means the chords are going to be equal. So these chords are congruent if a line that goes to the center of the circle from those chords are congruent as well. And again, keep in mind it's got to create a right angle for both of them. Okay? So again, pretty basic, pretty straightforward. It's really important for you to keep these foldables because that's going to give you all these theorems. So when you're working on your work, you'll use them and you'll realize which theorem you need to use, and then it's a pretty straightforward process. Okay, so let's look at these examples. Okay, so here we are given that it says find the indicated measures of in circle C. So we are given that AC, the diameter, is perpendicular to this chord right here. So based on the theorem that we just said, if this is perpendicular, then that means that it's bisecting these 2 chords, or this chord right here. So it's bisecting, which means these are equal to each other. So when we're trying to find the measure of BF, BF is going to be congruent to DF. So if DF is already 10, then BF is equal to 10 as well. Okay, and the same thing is true with the measures. We know that these measures are also being bisected, so those have to be equal to each other. So that means that the measure of arc AD is going to be congruent to the measure of AB. So if the measure there is 72 degrees, then the measure of AD has to be the same, which is 72 degrees. Okay, and then our last one, it says in the diagram of circle P, it says PV is congruent to PW. So now it's telling you that these are the same, meaning they're equidistant and they're a right angle. Based on the theorem we just said, it means that the chords have to be congruent. So now we can answer our question. It says if QR is 2x plus 6 and ST is 3x minus 1, solve for QR. Well, we now know that the chords are equal to each other. So we can set these equations equal to each other because if QR is 2x plus 6 and ST is 3x minus 1, we know that QR and ST are equal to each other. So what we do is we set those equations equal to each other and we solve. Minus 2x minus 2x. So we're left with 6 equals x minus 1. Add 1. Add 1. We're left with x equals 7. Now, that doesn't answer our question. It doesn't say solve for x. It says solve for QR. So we need to plug our 7 back into our equation. So that's exactly what we're going to do. We're going to plug 7 back into the 2x plus 6. So it'll be 2 times 7 plus 6, which is equal to 20. So QR is going to be equal to 20. Okay, so that will wrap up section 10.3. So don't forget to take your Edmodo quiz, and I will see you in class. Make sure you bring questions that you have with this. So see you then.